Hello guys. In last lecture we had seen was to define the notion of stability and related to transfer function, or how does transfer function have, or how does transfer function have any information on stability. And we characterize by saying that if any pole are strictly on left half of a plane, then my systems are stable, right? And then we also had some special characteristics when there are repeated complex conjugate root, how the system goes to unstable behavior. And even when you just have a single pair of complex conjugate poles, the system was defined to be marginally stable, right? And all these involve computing root of some higher order polynomial, could be 6, 7, 8 depending on how many poles there exist in the system. So now we will try to find an algebraic way to see if there are better or maybe more efficient tests of finding out the stability of system. So we may not be directly interested in extraction of location of poles, but an answer to whether the system is stable or not would be enough for the initial analyzing purpose. So what we will do today is to just look at the polynomial or fairly higher order, for which we could just compute root by hand. What are the methods which were involved, historically over time. So this method is typically referred to Routh Hurwitz criteria. So we are again interested in transfer function analysis, where I have a numerator polynomial of m and n is my denominator. N is usually or typically greater or equals to m, right? And then character equation, which essentially what happen is denominator, and that is equivalent to 0. So this referred to as characteristics equation of the system. No matter if your system is open loop, if you are doing on open loop analysis or even a closed loop analysis, we will formalize this characteristic equation shortly. But at a moment you just interested in denominator of given transfer function, for which we are interested to perform the stability analysis. So definition of stability leads to us to test which says, or which asks, suppose this was the question, are there any roots of system on right hand plane? If the answer is yes, then my system is unstable. Okay, so let us do some steps here. So QS is a polynomial here, which I can write in this way as a product. So this will have some roots. Let me call those roots as P1 to Pn, and these roots are the poles of my system. So if I expand this expression of poles, the expression would also something like this, right? And again in decreasing power of n until decreasing power of s until you reach n equals to 0. Okay, just to simplify this, what happened when there are 3 poles, right? Then this expression of QS, if I assume QS, let assume 3 would be equals to 1, then S minus P1, S minus P2, S minus P3, and this would expand to following like S cube minus S square, P1 plus P2 plus P3 plus S P1 P2 plus P2 P3 plus P3 P1 minus P1 P2 P3 S is equals to 0. Okay, so stability says that all the poles should be on left hand side. Means if we assume P1 P2 and P3, they should be having a value less than 0. So let's just for simplicity assume that there are real even though if they are complex, nothing much would change, right? So if p1, p2, p3 are less than 0, then the entire number would be negative. Then the coefficient of s there need to be positive. This should be positive, right? Similarly p1, p2 both are negative, p2, p3 are negative, p3, p1 is negative, and all this product would be positive number. Similarly p1, p2, p3 are negative, their product would be negative number, and this minus will make it positive. So what does the first observation says, right? If I have a polynomial like this, and if I want to observe, or if I want to say something about the location of poles in stable region, the coefficient of this should be non-negative. This one of the necessary condition. It may or may not satisfy, that we will see little later. And the coefficient should well be, they should have same sign, possibly it should be minus, 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 and all the time that could, or that also allowed, because you just equate to 0 and then all minus will become plus. Okay, so the first observation just by an expansion like this, and keep in mind that stability would means that the poles are on left hand plane. Okay, which would lead to us to say the necessary condition is that all coefficients are non-negative, right? And it could be a equals to 0. So what if if this is true, all the coefficient would be positive, right? And the follow just for general condition of this polynomial, this is the general expansion, then it for n degree n. So some straight commutation here would show that the ratio, or like the sum of poles from p1 to p3 pn would be expressed as ratio of n minus 1 and then n an, and similarly the product of all. So based on again these observation here, we would say that all the ratio should be, coefficient should be non-negative, and same sign for the system to be stable. And I am just rewriting those conditions in terms of polynomial and just dividing throughout by an. Okay, and since our an we assume to be 1 for simplicity, I think this should be very straightforward to find out. Okay, so but these are just sufficient condition, these are necessary, right? These are not sufficient condition, these are just a necessary, right? So it can show that if I am dividing with an, it would look like this. Okay, for example, if I take a system which follow this rule over here, right? S cube plus s square plus 2s plus 8 equals to 0. Well, they satisfy all the conditions that the coefficients are all 0. Now does it guarantee stability? We will just compute the roots, and roots turn out to be minus 2. This stable guy, you have 0.5 plus minus j 1.936. okay, now this guy right hand plane. Okay, so therefore the system is unstable. This guy is on right hand plane because a is greater than 0. So the system is unstable even though all coefficients are positive. Okay, so this is the test that these things, all the coefficients are non-zero, is just a necessary condition. It will not guarantee things, right? However, if instead of plus here, if I have a condition like say s square s cube minus s square plus 8 equals to 0, it violates the condition that all guys should be non-negative, and this is definitely unstable if I am making one sign as negative. This is because I am violating the necessary condition. and then I have root computed, or at least check whether the root lie in complex plane Routh and Hurwitz. So I will tell you a story of this later on. They come up with the condition which was both necessary and sufficient for stability of linear time invariant system. So how does this go? Well, not do the proof of it, but we will just learn the technique. So the method has two steps. First, I will just generate something called Routh array and interrupt the array interpret the array in terms of location of poles in S-plane. So we will read the statement once, we see how the array goes. So I have a characteristic equation, I just write it into an array. I start with S power n and I take the coefficient here. I take a power n, S power n coefficient. Then I take minus 1, that is S. Look at the coefficient. I took this coefficient a n minus 1. I take coefficient, put it here, then I do all the coefficient of n minus 2, n minus 4, and so until here, and then n minus 1, n minus 3, n minus 5, until I reach the end of the polynomial here. Okay, so these two are given to me. How about the remaining row? So giving that Sn minus 1, Sn minus 2, so this number is Bn minus 1. Compute in the following way, means I take An minus An minus 1, An minus 2 minus An into An minus 3 divided by this term. Okay, similarly I can compute Bn minus 2. I will multiply An with An minus 5. Okay, and first I will compute An minus 1 into An minus 4 minus An into An minus 5 divided by An minus 1. Okay, so this is, I think you could just call this as a matrix, and see the numerator is just the negative of determinant of that matrix. Okay, so you just assume this as a matrix and see the numerator is just the negative of determinant. Okay, so I just divide it by this coefficient here. Okay, then keep on doing this in this recursive manner. Then I can have, how do I compute the third Cn minus 1? I start from here. Okay, so I have Bn minus 1, then into An minus 3 minus An minus 1 into Bn minus 2 divided by Bn minus 1, and so on. So all I do, all these steps, and what does this last statement tell me? So the last statement, I will just go to the statement once. Okay, so the last statement is this, that Routh Hurwitz criteria states that the number of roots of the characteristic equation with positive real part is equals to number of change in sign for the first row of the Routh array. So I will just go to the first row first, means I will just go over there once. So I have this first row, an minus 1, then go to bn minus 1, cn minus 1. So if there is a sign change in any of these number, if I am having any sign change, so my construction an minus 1 would be same sign. They could write with these, typically both would be positive. So bn minus 1 becomes negative, right? Then there is a sign change, so we will see that with the help of example. And then if this is plus, okay, this is plus, this is plus, this is minus, then this is again plus, means this is plus, plus, then minus, then plus. So you will see there is no sign change here, there is one sign change here, then second sign change here. So this sign change will tell you that there are, or they will tell you how many poles are there on right hand plane, and that's what again we will read the statement. So that the number of, I will just go to the statement once again. Okay, so that the number of roots of characteristic equation with positive real part is equals to number of change in first column sign. So it will not tell you the exact location, but it will tell you first test in my system stable or not, or all the roots of characteristic equations are on the left hand half plane or not, or if they are on right half plane, how many are on right half plane, and so on. Okay, now next is, I will see the process till, I will continue this process till I reach S0. So you can just keep on computing this, and this array will reach until S0. And this is, you just look at this column, you check if there is any sign change in the first column. Okay, if there is no sign change, then my system is stable. If there are sign change, then there are roots of the characteristic equation on the right half plane. How many are there? That will depend again on number of sign change. Okay, so just to repeat, for a system to be stable, it is sufficient that all elements of the first row are positive. Again, this is, we will see why it is just a sufficient condition. If this condition is not met, when the way, if there is sign change, the number of root with positive real part is equals to number of sign change. Okay, so if you just look at this, I will go from an to an minus 1. Okay, I ask my question, is there any sign change as I go from an to an minus 1? No. And again, when I am going from an minus to bn minus 1, I keep on asking the question, is there any sign change? If there is sign change, and when the answer is no, then I can conclude that the system is stable. And if there are sign change, and if the answer is yes, I can say that the system is unstable. And the number of times the sign change, that is equals to root on right hand plane. Okay, so just as an example, so I start with fairly simple looking polynomial, s cube plus 4s square plus 9s plus 10, everybody is of same sign. So this is the necessary condition is met. So let go about drawing the Routh's table. So I start with s cube, which is the highest order of the polynomial. So I just have one, I will just once, this is 1, and then I will have 1 here. Then I go to s square, and this is 4. So Sn minus 1 is here. I'm looking for s power 1 now. So this is 4. S power 1 is here, 9. Then I will apply 10 here. Okay, so I will just compute how do I do this. Okay, so 4 times 9 minus 1 times 10 divided by 4. So 4 into 9 minus 1 into 10 divided by 4. So I get number here 26 by 4. Then 10 here, just by looking at the formula for Bn minus 1, Cn minus 1 in the previous slide. Okay, so what question do I ask? I just look at this column. Okay, and I ask, is there any sign change from 1 to 4? The answer is no. From 4 to 26 by 4, the answer again is no. Then 26 by 4 to 10, the answer is again no. So all there is no sign change, no sign change, no sign change. Therefore the system is stable. So all the elements of first column of Routh tables are positive, hence my system is stable. So I calculated roots of the equation also over here, which are all negative real parts, hence the system is stable. Okay, now in case of unstable thing, so you have x cube plus s square plus 3s minus 5. So this is again, inspection is unstable. Okay, let's just verify that with Routh's guide. Means I just calculated the roots, one root is positive, so obviously this is unstable system. I will just verify this thing with Routh's criteria. So I just do x cube, that is 1, then s 1, this is s square, this is s 0. Okay, I write this from characteristics equation. Okay, then I just find the sign change by, first I will calculate. So it is 1 into 3, 1 times 3 minus 5 divided by 1, it will be 8. So I wrote it over here 8. Again 8 times minus 5, this is 0. So I am not calculating that term, so divided by 8 will give me minus 5. Okay, and now I will see the first column. Is there any sign change? So here there is no sign change, there is no sign change. I will just clear it so that things will be more clear. Okay, so here you will see that there is no sign change. Here again my answer is no. Here my answer is yes, there is a sign change. Okay, so I have one, this is one guy is unstable guy, and okay, so these two stable poles, there is one sign change, so one pole on right half plane, right? So this is what the statement tells you. Okay, so not all elements in first column of Routh tables are positive, hence the system is unstable. There is one sign change which indicates one pole in right half plane. Okay, now let's do some more other example. So I have s 5 plus s to the power 4 plus 3, 2s cube plus 2s square plus 3s plus 15 equals to 0. And again necessary condition is satisfied that all the coefficients are same. Okay, so again I start constructing Routh's array. So I have x cube, I have 1, Then for s, so they see I have s5, so its coefficient is 1. Then I have a s cube, its coefficient is 2. Then I have 3s, its coefficient is 3. Again similarly s4 1, then minus 2 means s square, so it's 2. Then again 5. So this I am getting from my characteristics equation. Now something strange happen here. If I look at this matrix, well, determinant is 0. If I look at this matrix, the determinant is 0. So something strange is here, and these are like the special case, right, where there is a 0 in first column. What do? Do I just leave it here or say, well, there is no answer to this problem? No, there is a way out of this. If the first column of any row is 0, then just replace this by a small positive number, epsilon. Call it epsilon. Okay, small positive number. And this epsilon, the value of epsilon is allowed to approach 0. Okay, and it's like very small number, and then we compute the Routh table. Now this epsilon being small positive number, and then interpret the table for the stability. Okay, how do we do this? So the first term becomes undefined. The 0 in the first column is replaced with small positive number zeta. So the way we compute is, instead of 0, I substitute epsilon, which is considered to be greater than 0. This zeta over here is greater than, it is greater than 0. Then this element is computed as twice epsilon plus 12 over epsilon. I have 15 here. Then s power 1 turn out to be again doing this. Okay, and these computations, and now looking closely, look at the terms, right? As epsilon become very small, you could even take the limit as epsilon goes to 0. So this guy becomes negative number, right? If I put limit epsilon goes to 0, minus 15 epsilon plus 24 epsilon plus 144 epsilon to epsilon plus 12. So this will get cancelled, so it will be its total is negative. It is minus 44 divided by 12. So it's a negative number. This, and then last number becomes 15. Okay, so I just keep transversing here. So I say, well, there is no sign change 1 from 1, no sign change 1 from epsilon. Okay, epsilon is assumed to be positive. Since epsilon is assumed to be the positive, so this is also positive. Okay, then I go here, this guy becomes negative, this is positive, because if this is positive, this is positive, everything will be positive. Now this guy become negative, and again the last guy is positive. So if I see here, there is a sign change and there is another sign change. Here I am having one sign change, then another sign change. So since there is one negative element here, the system is definitely unstable. And then how many sign change are there? This is plus sign, one sign change, again sign to change to plus, so the system is unstable. Further, this table or this row tells me there are two poles of system in right half plane corresponding to two sign change. Okay, now let's see another example. So I have x cube plus 5s square plus 6s plus 30 is equals to 0, and then I put this in table. I pluck these numbers, say 1, 5, 6, 30. Okay, so there is some strange thing happening here. So this entire row is now going to be 0. If I am calculating it, it is 0, right? What do I do now? I really substitute epsilon, again epsilon, and do the analysis. Well, the answer is no, because you still again get encounter 0 if you do that, right? If this is epsilon, this is epsilon, again you will encounter 0. Okay, so what do we do here? So we will be little careful that if entire row is 0, we form something called as auxiliary equation or auxiliary polynomials. Okay, so with the row immediately above this guy, we will form an auxiliary equation from this row, this row just above that 0, 0, and then differentiate with respect to s. Okay, and then I will have then, so if this is a polynomial of order 2, and then I have something in order 1 here. After differentiating, the row of 0 of this guy is replaced with the coefficient of differentiated term of these differentiated auxiliary equations or polynomials with respect to s. Okay, so this is my auxiliary equation, 5s square plus 30 equals to 0. I am differentiating it, so now it will be 10 over here. Okay, so 5s plus 30, I differentiated 10s plus 0, so I will pluck in here. I take this 0 and I pluck it here. So it will, so new, or my new table now look like this, right? And that's Routh's array. So I differentiate, I take 10, then I proceed with the rest of computation, and then this guy is 30, then I again do the sign change. There is no sign change, no, and therefore I can conclude that the system is stable because all elements of the first row are positive. Okay, there is something little more here, right? That since the guy is entire row is 0, there is existence of pair of roots which are on imaginary axis. That is simply given by the solution of 5s square plus 30 equals to 0. You solve this, this will give you that exact location of roots on imaginary axis. So whenever the entire row goes to 0, then you detect a pair of root on imaginary axis, and now this is conjugate pair. That would be a conjugate pair. What if there are more of these auxiliary polynomials? So the auxiliary polynomial is essential. It has a higher order, is of course even number. Actually, it would have s to the power 4, s to the power 6, s to the power 8. These are the highest power, and then you could have all the other power, could be s square, s0. Okay, so here you could have s6, s4, s4, s2, okay, so on, right? It will be just have s to the power 6, s to the power 4, and so on. In this case, there are we see there are roots that are symmetric about the origin. Symmetric could under several conditions. Symmetric could be like here. So here we have -1, you could have +1 here, so they could be symmetrical, just like lie just on imaginary axis, positive j omega, negative j omega. There could be something like this also, right? you have 1 plus j omega minus 1 minus j omega. Okay, so this is minus 1 plus j omega. Okay, so there is symmetry about the imaginary axis. So if this is positive real part of the characteristics equation, then again up here you will have negative. So this again appear only when you know when some of these kind of things happen. Okay, so let's do another polynomial here. I have s to the power 5 plus 2s4 plus 2s cube plus 4s square plus 2 equals to 0. So I construct my Routh table. So I have 1 s to the power 5 is 1 2 1, then 2 4 2 sitting here. So when you have things like this, you could just even replace this, just divide this with its common factor. So you could have here as 1 2 1, and you can divide all of them with 2. So it will be same analysis, and you see the rows are of same numbers, therefore the entire row of cube will goes to 0. So what do I do now? I will construct my auxiliary equation polynomial, that is s to the power 4 plus 2s square plus 1 equals to 0, and even will be same even if you write 2s square plus 4s 2s4 plus 4s square plus 1 2, the things will be same. Then I am differentiating it with respect to s, which will give me 4s cube plus 4s plus 0. Okay, now I go here, right? So I just substitute the entire fourth row over here. Okay, so this would be 4 4, this is 4, this is also 4, and 4 is common, just I get rid of 4. I can write equivalent 1 1. Now I compute s square. Okay, what I get is again 1 1. Not surprising because this is 1 1. Okay, so there is another 0 entry here. Now I construct further one more auxiliary polynomial. So I keep on doing it each time I encounter a row which has entries which are completely 0, and then I take this guy, second polynomial, I call it a prime. Okay, s square plus 1 equals to 0, differentiated with respect to s, 2s I will get. So there is no sign change. You can say, well, this system is stable. Well, for my stability theory we had learned something, right? That if, let's just draw the complex plane here. Okay, I have sigma, I have j omega, everything here is stable. Okay, so if I have a root where this is plus j minus j, I called as marginally stable. If I had something like plus 2j minus 2j, okay, that was we derived that these root actually leads to system to instability. Okay, now where is this? So I know there are 4 roots on an imaginary axis, 2 coming here because of first auxiliary equation, then 2 coming here because of second auxiliary equation. So let me calculate the roots. So s, if you just go back, one is s square plus 1 and another auxiliary equation is s4 plus 2s square plus 1. So when you solve it, you are getting roots like this. So s square minus 1 equals to 0 would give me root as s is equal to plus minus j. I have 4 roots which are plus j, minus j, plus j, minus j, and these are repeated roots on imaginary axis. Okay, then we conclude that the stability analysis class, that when I have repeated root on imaginary axis, then the system goes to being unstable, and therefore we concluded that the system is unstable. Okay, so these are special cases which we need to be careful of while we are computing stability. So we just need to be remember all those cases which we analyzed during the stability. Okay, a bit of history here. So where did all this start from? So this had the roots of Routh Hurwitz stability criteria was developed somewhere in 19th century when Maxwell, now the famous guy of Maxwell equation, they become interested in stability of dynamic system, and this Maxwell was motivated by the analysis of centrifugal governors, which was essentially invented by James Watt for his steam engine. So Maxwell was a first to make some initial guess around these things. He was first to provide theoretical analysis to feedback system using some linear system, so linearized differential equation. So this was the governors look like. So this is the picture we took from Wikipedia. So what does Maxwell say in his paper? So this is from his paper 1968 called on governors, which appears in proceeding of Royal Society of London. You still download it. So what Maxwell said, that the condition for stability of the governor, so this guy here is mathematically equating to the condition that all the possible roots, they still didn't define this because they didn't have notion for right half plane, left half plane, stable roots, unstable roots, marginally stable roots, okay, and so on. So that's all the possible roots. So instead of that, the stability was equivalent to the condition that all the possible roots and all the possible part of impossible roots of a certain equation should be negative. So this is little misleading because they didn't have any formal terminology to define. So essentially he meant that all root must be negative. So possibly roots were all real roots, they shall be negative. Then you could have impossible root which are imaginary. You say that the possible part of imaginary roots were real part, and these possible part of imaginary roots, so of the impossible root says, for an example, minus 1 plus j omega was regarded as impossible roots, but this was possible part of all these should be negative. And then Maxwell could do this for third order equation. So he said, I have not been able to completely determine these conditions for the equation. So he said that I have not able to completely determine these conditions for the equation of higher degree than the third. And then he posed his problem to set of mathematicians. Okay. Then, so this analysis by Maxwell leads to the subject of Adams Prize in 1977, with Maxwell was being as one of the examiner. Then the problem which was thrown at mathematicians was to find a general criteria for dynamic stability or system, right? And then later Edward Routh, in his essay called A Treatise of Stability of a given system, given state of motion, presents this condition which we learned just now for Routh's table. So parallelly, and not surprising, from Russia there were also people working in similar area, and then the result again of a steam engine with governor. They were used by some guys to design water turbine governor, and then Stadlow to design with his collaboration at ETH in Switzerland, independently also arrived at stability criteria, and these two actually involved independently, right, using some different methods. And to honor this parallelly evolved result, the stability criteria is now what we know as Routh Hurwitz stability criteria, and this is a little interesting story of how the stability criteria evolved. So what we had, all these are the papers which we could actually refer to see in the history of all these analysis of stability of differential equation. What we learned so far is that Routh Hurwitz criteria, some special cases of what happened when there is 0 in one of the entire row, what happened if there is 0 in entire row, and then did the analysis of Euler equation. Okay, now in next topic, so at the moment we just look at the analysis only in terms of roots of certain polynomial. So in next analysis we will give it to a little more control flavor analysis, this in terms of feedback. Then we will do things related to sensitivity. We will also slightly introduce the concept of relative stability, what relative stability means, and we will see if we could solve some of those relative stability criteria or relative stability problems using Routh Hurwitz criteria. Thank you.